Now that we have done our work with finding what radian measure is for a measure of a central angle, and we also have a connection between the radian measure and the degree measure, we can actually look at our first application of radian measure of an angle with this concept of angular speed and linear speed. The definition of linear and angular speed of a point on a circular path. Well, if you have a point that moves on a circular path with a radius of r, so the circle has a radius of r, at a constant rate of theta radians per time. So right away they're reminding us that our theta that we use for our angle has to be in radians per time. Then it's linear speed. So the linear speed is the length of the arc that it has, the distance the point travels, divided by your time, whatever your unit of time is. So S is your distance that the point travels. So that's like that arc on the outside of the circle. And remember from a previous video that the length of an arc on a circle is equal to the radius of the circle times the central angle theta measured in radians. So that's why we need to have it in radians. Now think about distance even when you're driving your car. When we say we're driving our car at 55 miles per hour, it's the distance we travel. Per is for the fraction bar, every 1 hour. So we go 55 miles per every 1 hour when we're saying that. And so that is like our linear speed, and that's the same concept that's talked about here, because you think like if you drove over wet paint with your tire and then you started right at the measure of which that paint was being transferred onto the pavement that you were driving on, and you took a stopwatch from when you started having that paint work or lay down on the pavement until you stopped, then the distance of that line of paint divided by how long it took you to make that line of paint then would be your linear speed. Now the point's angular speed, this is the angle at which it's spinning on the center of the circle that's making that path. Omega is the Greek letter that we use for angular speed, and our angular speed is measured by the angle measured in radians divided by the time that we've done that. So our common units of our angular speed, so when I'm talking about omega, the angle per whatever time we're using it in, usually those measurements are like RPM, revolutions per minute, if we're doing revolutions per second, or like radians per minute or radians per second. Just from convention, if they say RPM, they mean revolutions per minute. They don't mean radians per minute. So when we talk about the initialization of it, you just have to be careful to remember that your revolutions per minute is the initialization of the RPM. And that's a standard along a lot of different applications, and we need to keep that standard so that it doesn't conflict when we look at connections between different topics. Now, linear speed and angular speed have a connection between them. So if I look at my linear speed is the distance the point travels per time, but the distance the point travels per time is from that formula that it is equal to the radius times that central angle measured in radians. Then if I replace this S with theta, or r times theta, so if we look at that equation and we look at V is equal to, replace S with its equivalent of r times theta, and that's over t, and we compare it with the angular speeds formula, we see that this is r times theta divided by t. Well, I can write that as r over 1 times theta over t. and r over 1 is just r, and theta over t is my omega. So I can think of the connection between the linear speed and the angular speed as the linear speed is equal to the radius of the circle times the angular speed, as long as you're looking at that angular speed in radians per time. Because my theta had to be in radians, we're talking about this connection between it being in radians per time. So now what we're going to do is clear the board and then do some examples. The first examples I'm going to do are going to be kind of connected with, what if I want the angular speed and I just want it in a different unit than it currently is. So in the setup of the problem, they're not giving me a linear speed and an angular speed and asking me for the radius, or two of these three components asking me for missing one. They're just actually asking for a angular speed when they give me a unit that's not quite the units that we want. And then once we practice on that a bit, we'll go to do some applications where I am working with the connection between linear speed and angular speed. Linear speed is equal to s over t, where s is the length of the distance that the point has traveled per time, and s is equal to r times theta, where theta is in radians. The angular speed is omega, and that is theta over t, so the amount of angle that has been in radians divided by time. And then the relationship that ties the two of those together is that the linear speed is equal to the radius of the circle times the angular speed. So these are the three formulas that we need to look at when we're trying to decide what to do with each of these problems. So I wanted us to just have them here so we could look and decide which one to use. The first problem, as an example, says the tires of a car are rotating at 100 RPM. So remember, by convention, RPM is revolutions per minute. Find the angular speed of the tires in radians per minute. So here it's talking about the rotation of the tires, so that's angular speed. It's talking also about the finding the angular speed in radians per minute. So I have where I'm just really going with the radian speed, or sorry, the angular speed, and I'm just changing units. So the formula that we're going to use out of these three choices is our angular speed one here, because I'm not doing a connection between the linear speed and the angular speed. I'm just specifically talking about the angular speed. Now I have to start that they're traveling at 100 revolutions per minute. So I want to set that up as the fraction to get ready to do my unit conversion. So this is 100 revolutions per, remember per is where your fraction bar goes, every minute, per every 1 minute. So part of this whole process is just being comfortable with interpreting what the units are telling you. Now I want to multiply by a unit conversion factor where I get rid of the units I don't want and bring in the units I do want. A different unit then will be a different unit than the denominator. But the overall value is 1, and when I take something times 1, I'm not changing its value, I'm just changing the way it looks cosmetically. So we want to go to radians instead of revolutions per minute, so I'm going to stay in the minutes. So here I have just my 1 unit conversion where I want the revolutions to come out and the radians to come in. And remember, when you're setting up your unit conversion factor, wherever the unit is that is currently the one you don't want, currently the one you have, but you don't want it anymore. So wherever it is in the fraction, you have to go to the opposite place of the fraction to be able to remove it. Now, what's the relationship between radians and revolutions? This is going back to the circle that we talked about when we learned about radians. So remember, from the beginning of the circle, all the way around to the end of the circle gives me my 2 pi radians. So 1 revolution is always equal to 2 pi radians. 1 revolution is equal to 2 pi radians. So when I look at where these words are, a revolution is all the way around, so that's bigger than a radian. I give that the 1. And how many radians make up a revolution? 2 pi radians make up a revolution. So then when I look at simplifying this, I have the common factor of revolutions that we'll remove. And I have 100 times 2 pi, so that's 200 pi radians per minute. So that's our exact value. Now, all the way through this course, you're going to want to, or your work with trigonometry, you want to leave your answer exact, and then after you have the exact answer, go ahead and approximate to what it is that they asked the approximation to be. Here it did not ask to give an approximation, so I'll just go ahead and leave it as 200 pi radians per minute. If it asked me to approximate, I would have to pay attention to what the rounding should be, and then take my 200 times the pi key. Don't just use 3.14 because that's an approximation, and if you're supposed to give your answer in more accuracy than that, you are going to not come up with the correct answer. So you want to use your pi key and take 200 times the 3.14159, etc., and get the value first and then approximate it after that. But here we're just going to leave it exact. All right, so that one just wanted to give angular speed when they already had given me angular speed with just a different unit, and also didn't have anything in there about the radius of the circle, didn't have anything in there about the linear speed. So that's why I knew it was just staying within this angle speed formula. Let's do the next one. A truck has 34-inch diameter tires, and the angular speed of the tires is 732 RPM, revolutions per minute. Find the linear speed. So in this problem, it's angular speed is given to me, linear speed is asked of me. I have something about where I can get the radius of the circle of the tires. Find the linear speed of the truck rounded to the nearest mile per hour. So I'm going to get it exact, and then we're going to round it. So this does connect the linear and angular speeds. So I'm going to use our formula here that connects the linear and angular speeds. So V is equal to R omega. But the biggest thing is that it's not in the right units now, so this is a really big unit conversion problem. That's pretty much what these basically are. Sometimes we have to do a little bit of solving if they give me the linear speed and the radius, or they give me the linear speed and the angular speed. I'll have to solve my equation. But in this one, they give me a way to get my radius, they give me a way to have my angular speed. I just need to get these in the right units to give the linear speed in the requested units. All right, so, well, if my tires are given to me as 34-inch diameter tires, then that means that they have 17-inch radius. So my radius is 17 inches. And I'm going to put that over 1. And I'm just going to use the dot between the fractions as you go. Sometimes you'll see where there'll be a horizontal line, and they'll just be vertical lines at separating off the numerator and the denominator of the fractions in your unit conversion. If you're comfortable doing that from your science classes or from other settings, go ahead and do it that way. It's just a matter of preference. It's not one's better than the other or more correct than the other. So that's my radius. But notice my radius is in inches, and ultimately I want to give my answer in miles. So there's a unit conversion that's going to happen there. Now my angular speed right now is in revolutions per minute. Remember, that's one of the units for angular speed. So right now I have 732 revolutions per every 1 minute. supposed to have my central angle in radians per time to be able to get the thought of that paint being laid down on the pavement. And my time needs to be in hours, not in minutes. So there's several different unit conversions we have to focus on. Now I'm going to start with getting out of the revolutions and into the radians because that's one that would be easy to forget. So I want to take care of that early. Remember, if the revolutions is in the numerator and you want to get rid of it, you need to have it in the opposite part of the fraction in the unit conversion so they remove as common factors. I can take out a revolution and put in radians by remembering that 1 full revolution is 2 pi radians. So 1 full revolution is 2 pi radians. So now my revolutions are out of there, and that's better. Now in terms of, let's do time, I guess, next. So let's do the time conversion. The minutes are currently in the denominator, and I don't want units of minutes. So to get them to cancel, I'll have to put minutes in the numerator. And I want to bring in hours. So I'll put the hour in the denominator. An hour is longer than a minute, so I give it a 1. And how many minutes are in an hour? Well, 60 minutes are in an hour, so that's going to be 60. So now my minutes units will cancel. And then lastly, I'm actually going to do 2 different conversions to get from inches into miles because I don't off the top of my head know how many inches are in a mile, but I know how many inches are in a foot. There's 12 inches in a foot. And I know there's 5,280 feet in a mile. So if I go from inches to feet and feet to mile, I ultimately get there. So our next unit conversion we're going to have, inches are in the numerator, I need them to cancel, so I'll put it in the denominator. And I'm going to bring in feet. So 1 foot is the same as 12 inches. So then the inches will cancel. And then lastly, I need to take out the feet and put in mile. And a mile is bigger than a foot, and it takes 5,280 feet to make up a mile. So now the feet units cancel, and oh, that's right there. Okay, and notice radians is in there, but that is part of the assumption of 2 pi radians. So we're not actually going to write the radian part of the units in our final answer. But as far as units go, I have my mile in the numerator, the fraction bars per, and the only unit left in the denominator is hour. So I will get my linear velocity in miles per hour. Miles per hour. So what we're going to need to do is to go ahead and multiply this out and then give our approximation to the nearest mile per hour. So when you go through and you multiply through the numerator, keep the pi to give your answer exact first before you go to an approximation, and then divide by. Don't forget when you're doing your division to open parentheses to do the 12 times the 5,280 close parentheses to make sure you divide by that entire quantity. Our exact value here is our linear speed is 1,037 pi divided by 44 miles per hour. And then when we go ahead and calculate that out, it rounds to the nearest mile per hour of 74 miles per hour.